Hi guys, Dr. Musk back again. So let's talk through the last part of chapter 13. We're kind of skipping 13.7 and 13.8. We'll get to some of that later on, all right? But for right now, I want to skip ahead to 13.9 where we're talking about aromatic compounds. So aromatic compounds are compounds that contain benzene rings or things that have similar properties to benzene rings. So defining what aromatic means is kind of difficult with the level of theory that we're at in Chem 131. So things that are like benzene rings and benzene rings is kind of how I'm going to define it. And notice that in benzene rings, all 6 of those carbons are I'm not even going to use hybridization. I'm going to say that each one of them has 3 electron groups. So all of those carbons around the ring are trigonal planar, which means that that entire benzene ring is on the same XY plane. It's flat, just like the paper that this slide is printed on is, all right? So notice that there are 2 different ways that we could represent benzene, all right? And the only difference between them is the position of those 3, what I'm calling double bonds around the ring. In reality, benzene doesn't have any double bonds or any single bonds. The reason why is when there's more than one proper way to represent a molecule with a Lewis structure, where the only thing that changes is the position of electrons, then we have to remember that the reality is that neither one of those individual Lewis structures really does a great job explaining what that molecule is like. Instead, it is a hybrid of all of those structures, all right? So even though in those individual drawings we see double bonds and single bonds, the hybridization of those 2 drawings together, taking them as a whole, means that this is not really a carbon-carbon double bond, and that's not really a carbon-carbon single bond. In other words, it's an average between those 2 structures. So all of those carbon-carbon bonds around the benzene rings are actually carbon-carbon 1.5 bonds. Interesting, huh? Yes, some people shorthand benzene rings like this. I hate that, so instead just draw them the way that you're supposed to, all right? There are reasons why I don't like to shorthand benzene rings. So the important thing for us to remember is the fact that there is resonance in those benzene rings means that electrons in that ring are delocalized. In other words, they're shared over multiple carbon atoms. So because of that, benzene rings have lots and lots of stability compared to other kinds of alkenes. In other words, they are not nearly as likely to react in chemical reactions as other kinds of alkenes are. So for example, if we put ethylene, a normal alkene, in with Br2, we would get a halogenation product of that reaction, all right? So the halogenation product is we add halogens to both of the carbon atoms where the carbon-carbon double bond was. If we just add Br2 to benzene, those don't react with each other at all. So benzene looks like it has carbon-carbon double bonds, but in reality it has carbon-carbon 1.5 bonds. They're not nearly as reactive. So first of all, when we discuss aromatic compounds like benzene, we need to talk a little bit about how to name benzene and things that are derivatives of benzene. So first of all, if we have a substituent group on benzene, that's really easy. We just name the substituent group and then give the parent name benzene afterward. All right, so you can see examples of that here. There are some mono-substituted benzenes that have common names. So if we have benzene with a methyl group attached to it, the common name for that's actually crept into systematic naming is toluene. So very often, if we have a toluene that has another substituent group, then we can name that as a derivative of toluene. So for example, what if I had a bromine atom sitting right there on that molecule? We could name this as a derivative of toluene. If we take that CH3 as carbon 1 and count around to the bromine, we get to it at carbon number 3 of the ring. So this would be 3-bromotoluene. So we could do the same thing with a phenol or with an aniline. All right, so aniline is if we have an NH2 group attached to a benzene ring. We call the whole thing aniline. When we have di-substituted benzenes, if we have two of the same substituent group, we can talk about them as a 1,2 di-substituted benzene, so 1,2-diethylbenzene in this case. Or we can talk about the relative positions of those two substituent groups by using the prefix ortho for that. So ortho literally means 1,2, all right? That's sometimes shortened to just the letter O. Meta is if we have two substituent groups that are the same that are at the 1 and 3 positions, all right? So that's often shortened to M. Para is when we have a pair of substituent groups at the 1 and 4 positions that are identical. So that's often shortened to P. And if we have two different groups on the benzene rings, I tend to use the numbers instead. All right, so I would call this 1 bromo, 2 chloro benzene. But you can use the ortho, meta, para nomenclature if you just alphabetize the two substituent groups. So this would be ortho bromochlorobenzene. That's totally fine if you want to say it that way. Or because ethyl comes before fluoro and the two are at the 1 and 3 positions here, we could, instead of saying 1 ethyl, 3 fluorobenzene, call this meta ethyl fluorobenzene. So we can also use that second substituent group with this ortho, meta, para nomenclature if we are naming it as part of one of those benzene derivatives that has its own name. So a toluene with a bromine at the other end at carbon number 4, we could name that 4-bromotoluene, or because the bromo is at the 4 position compared to the toluene CH3 at the 1 position, those two substituent groups are para to one another, so we could just call this para-bromotoluene. Because the chlorine and the OH group of the phenol are at the 1 and 2 positions, we could refer to this as 2-chlorophenol, assuming that the 1 is where the OH group is, or we could just call it orthochlorophenol. Either one is perfectly fine. When we have more than 2 substituent groups on a benzene, we just have to make sure to number them to give the lowest possible numbers. And if it's one of those derivatives of benzene that already has its own name, like toluene, then we would start counting carbon number 1 at the carbon that had that substituent group that gave the benzene derivative its name. So let's do a few examples of that, all right? So here we see an ethyl group, a propyl group, and a chloro. So ethyl, propyl, and chloro. In terms of lowest possible numbers, the lowest numbers that we can count around here is 1, 2, 4. And then in terms of alphabet, chloro comes before ethyl, comes before propyl. So anyway, this ends up being 4 chloro, 1 ethyl, 2 propyl benzene. So let's do another one of these where we're doing a derivative of benzene that has its own name. So what if we had something like this? Now note that the NH2 attached to a benzene ring is one of those special derivatives of benzene that has its own name. We call that aniline, all right? So this aniline, no matter which way we count, we get to the first substituent group at carbon number 3, all right? And actually, I'm going to make the two substituent groups different from one another. And I'm still counting the correct way because we would rather have ethyl, which comes alphabetically sooner than methyl. We'd have ethyl at the lower number. So here, we just have to name the substituent groups that aren't part of the aniline. So this would be 3-ethyl, 5-methyl aniline. And you can see another example of an aniline here, where if the aniline starts numbering at the 1 where that NH2 group is attached, we get to our second substituent group as quickly as possible. All right, so this would be 2,5-dichloroaniline. There are other aromatic compounds that have more than one ring. It's even possible to have an aromatic compound with less than 6 atoms in the ring, but we don't need to worry about that too much. So benzene is the aromatic compound that I really want you to recognize. And there are lots and lots of benzene rings all over the place in drug molecules. So you can see a few examples of those. In sunscreens, all right, so para-aminobenzoic acid is the most common ingredient in sunscreens. And then benzopyrenes, these are carcinogenic compounds that form when, for example, you overcook meat, or when any source of carbon just gets charred to hell. You end up with benzopyrenes as a product of that in small amounts. They're very carcinogenic. And I think we're going to be finished at this point because the video is getting a little bit long. So tune in for our next video where we talk about the important reactions of benzene.